So we've been working on some financial situations, and the first thing we did back in the day was simple interest, which is not a very common thing in the real world. And then we started working on compound interest, which where instead of in simple interest, where it's the original amount that gets added every time, a percent of the original amount that gets added every time. Now compound interest adds the interest in, and then you have a larger amount that you calculate the interest on for the next month. And what we figured out is that our compound interest formula is that the future value of your money is the present value times 1 plus the interest rate over k, and to the k times the number of years. And when we wrote this formula out, what we were talking about is how the R is the percent interest. The K is the number of compounds per year. And then the N is the number of years. The PV is the initial deposit. And then the FV, the future amount, is the ending money. And the reason there's the 1 in there is because this represents that you keep 100% of the original, and then the plus, this chunk here, represents that you add a percent, add R percent, that's why there's the over 100, but you don't add the whole amount every time. The reason it's divided by K is because if you get the interest 2 times a year, you get 1/2 of the interest each compounding. If you have 12 compounds a year, you get 1/12 of the interest. So you add R divided by K, and then up here, it's you do that K times per year. Okay, so that was just to sort of review our compound interest formula. But in the real world, what often happens is that you're actually making more deposits over time. It's very rare, although it does happen, but it's very rare that you just put a chunk of money away and just wait on it. That's like a certificate of deposit or something like that. So in the real world, a lot more often you'll have a situation that our textbook calls an annuity. This word can be used in a couple different ways in the real world, and so I'm going to focus on the definition here, where you have an initial deposit plus regular additional deposits plus an interest rate. So this may be a situation like you receive $1,000, maybe as a gift from a long lost relative who passes away, and then you decide, I'm not just going to put $1,000 in, I'm also going to save, say, $100 extra a year. We'll just do that as an example. So let's say you have $1,000 gift or inheritance, and then you also save an extra $100 per year. And let's say that you find a savings account that pays you 2% interest per year. So just like how we started out compound interest, where you have the money and then you take the interest, then you add them up, and then we realized that taking the money and adding the interest could actually be written as a geometric sequence, could actually be written as 1 plus the interest times the money, and that we could write that as like an exponential function. We're going to see something here. I'm going to build it up to a nice formula. So here's how it starts out. You start out with $1,000, and then you multiply that by 1 plus 0.02, because that's your 2%, and then you add $100 onto that. And then that's what happens after a year. You get your 2% interest on what you had in the account, and then you add $100 more. Well, what's going to happen at the next year? Well, first let's get this intermediate step. So 2% would be $20. So you have $1,020 from the 2% plus 100, so $1,120. And then the next year you have 1,120, 2% of that plus another 100. And this right here, you can see, I hope, that there is some repetitive structure going on. I'm going to try to build this up. So here's what I typed into the calculator, 1242.4. And so 0.40, so 40 cents. And then again, next year, 1242.40, 2% interest plus $100 more equals whatever. And you can see that this process, although it's not that hard at any one step, if I asked you to go 20 years into the future, you probably don't want to sit there and write out all of the intermediate steps. And so because there's this similar pattern of the terms that I'm using, I'm going to try to build up a formula that allows us to predict any value. So what I notice is that the answer here matches with this. And what that means is I can replace the number 1120 with this original expression right there. And then I also notice that the answer here shows up right here, which means I can replace the entire expression here with the 1240. So I'm going to do that. I'm going to replace both of them. It's kind of like Russian nesting dolls. You've got one inside of the other, inside of the other. So I'm replacing the 1242 with this purple box right here. But I'm also replacing the 1120 with this purple box right here. So it's going to start out with 1,000, 1 plus 0.02 plus 100. That is 1120. And 1120 is the part that starts at the beginning right here. So I'm replacing that as 1120, and then I'm plugging all of this in for the 1242. So I have 1120 times 1 plus 0.02 plus 100. That's what the 1242 is. And then all of that, I have to finish out the formula with the rest of it. Another 1 plus 0.02 plus 100 at the very end, no parentheses. Okay? Now, what I'm going to do is distribute. So let's create a little bit of space up on top for this distribution. And I hope you can see, even if you're not able to do this all by yourself, I hope you can see how there's just similar terms showing up over and over and over again. And that's what I'm doing when I'm distributing. So what I'm going to do is I'm going to distribute the 1.02 here, 1.02 there. And so that's going to give me 1,000 times 1.02 squared plus 100 times 1.02 plus 100. And then I have another 1.02 plus 100. And then we're going to distribute that again. Distribute, distribute, distribute. So I have 1,000 times 1.02 to the third plus 100 times 1.02 squared plus 100 times 1.02 plus 100. Now, what this means actually makes a lot of sense if you think about how the account works. The original $1,000 has 3 years of interest. The first 100 extra dollars has 2 years of interest. The next $100 has 1 year of interest. And the last $100 has not earned any interest yet. Okay? So this is what happens after 3 years. What would it look like after 4 years? Well, now we'd have 1,000, 1.02 to the fourth. This one has been in there for another year, so it gets to the third power. This one has been in there another year, so it gets to the second power. This one has been in there for 1 year, so it gets 1 year of interest, 2%. And then there's a last one that gets tacked on at the end, 4 years. So this is a little bit better because now, if I wanted to, I could write out the 20-year pattern. We would just have a bunch of 1.02s tacked on. The first number is $1,000. All the other ones are $100. Okay? So, however, what you can do is you can do even better than this. You can take the first part and leave it alone. This is just your regular compound interest. 1,000 times 1.02 to the fourth. But every other term has a 100 in it. And what you'll notice is all of the other terms are just a geometric series where you're multiplying by 1 plus the interest rate. So let me clear out a little more space here. What I'm noticing is that the first term is just your basic compound interest formula, which makes sense. Whatever money you put in the account at the beginning is just going to sit there and earn interest. And then the rest of it is the sum of a geometric series. And when I look at the geometric series, what I want to do is identify what the first term is and what the R value is. And so I remember that the sum of n terms is the first term times r to the n minus 1 over r minus 1. Okay? And so if I do that, in this example right here, I have 3 years. And so I could do it is 1 times 1.02 to the 3 minus 1 over 1.02 minus 1. And I can use that same idea for any number of years. And so what this leads to is a nice formula. I'm going to skip ahead a little bit and just sort of generalize the formula here. That the future value in this annuity is equal to your normal compound interest formula, the present value, 1 plus your interest rate to n years, then plus your regular deposit, sometimes called your payment, PMT, so a lot of times how they'll abbreviate the payment, and then the sum of the geometric series, which looks like this, r to the n minus 1 over r minus 1. Okay, so this is one version of the annuity formula that you can get. There are other ways you can rearrange the formula, and there's also the finance app on the calculator that you can use to calculate these things. But I wanted to show you that example of the annuity formula and where it comes from. And hopefully you could see the structure and how I was going through and just noticing things that were the same one step at a time. So thanks for watching. Please comment and let me know if anything was confusing.